In this work, we present particle grid neurodynamics for learning deformable object models from depth images. Modeling deformable objects is crucial for manipulation tasks involving soft and flexible materials. By utilizing visual observations and action inputs, a dynamics model can predict the object's next state, enabling model-based planning and enhancing physical reasoning. The state-of-the-art learning-based method for modeling deformable objects is graph-based neurodynamics, which represents objects as sparse particles and robot end effectors as additional particles connected by spatial adjacency graphs. Then, it uses graph neural networks to aggregate information among nodes and generate motion predictions. However, GBND methods face key challenges. They require expert knowledge for graph construction, struggle with global motions due to limited message passing steps, and cannot handle partial observations. To overcome these challenges, we propose the particle grid neurodynamics model, which represents object states as dense particles for future prediction. First, the model encodes particles and predicts grid velocities with a point encoder and a neural velocity field. The model then incorporates robot actions and collision boundaries with grid velocity editing. Finally, the velocities are transferred back from grid to dense particles with a grid-to-particle interpolation, providing the next step per particle velocity predictions. Given initial state and action, our model more accurately captures deformations compared to the GBND baseline, resulting in closer alignment with the ground truth. Our approach also effectively handles other deformable objects such as rope, plush toy, paper bags, boxes, and bread. Our particle grid dynamics model can be combined with 3D Gaussian splatting reconstruction for action condition video prediction. Our approach offers improved motion prediction and delivers higher visual rendering quality compared to the GBND method. By utilizing high-density Gaussian splatting reconstruction from phone-scanned videos instead of sparse-view inputs, our method can achieve higher rendering quality, enabling realistic simulations of robot-object interactions. Our particle grid model can also integrate with model predictive control for planning. Here, we show that our method achieves lower final error compared to the baseline in rope manipulation and cloth lifting. Also in box closing and plush toy relocating. Thank you.